guess it's time. If y'all ready. I'll stand up here, I'll project, it'll be awesome. So, Giordano Bruno. Thus is the excellence of God magnified, and the greatness of his kingdom made manifest. He is glorified not in one, but in countless sons. Not in a single earth, a single world, but in 1,000,000, I say, an infinity of worlds. That was Giordano Bruno writing on the Infinite Universe and Worlds in 1584. Giordano Bruno thought that there were more suns than ours, that there were more worlds orbiting around those suns. But it took 400 years before we were able to confirm that fact. So this is Alexander Goldstein and Dale Frail. And in 1990, they discovered what they thought was a planet orbiting around a pulsar. So they were working, where were they working? Arecibo Observatory. Sorry, I have a lot of things to do, and this is the largest water bottle I've ever had, so look out. So they were working at the Arecibo Observatory, and they discovered, they were looking at pulsar PSR B1257 plus 12. And the thing about pulsars is they are highly magnetic, and they're spinning, and they pulse. When it was discovered in 1960, they thought that they were getting radio signals from an alien species because it was so regular, and it came, just beat after beat after beat after beat. And eventually they discovered that it was a pulsar, and when these things spin, they essentially send out like a lighthouse, little signals, and they're very regular. But what Goldstein and Frail discovered was this particular pulsar was sending out signals, and the timing varied just a little bit, not a lot, but a little bit. So they dug more into that and decided, hey, that may be a planet orbiting around that pulsar, dragging it around, making that pulsing signal that it's sending change times. So they were actually kind of surprised about this because pulsars, they start out coming from supernovas. The idea is you've got a supernova and it explodes and it leaves behind this tiny core, this tiny magnetic star that's spinning. And so researchers thought, supernova explosion scrapes all planets out of its solar system because of that explosion. But Goldstein and Frail were very careful about talking about this planet because a year earlier, there were a team led by Matthew Bales and Andrew Lynn, and they published a paper in the journal Nature and said, we found a planet around pulsar. And then in 1992, 1 year later, about the time that these guys were discovering this planet, those guys had to come back and say, turns out it wasn't a planet. It turns out they had neglected the fact that the Earth's orbit around the sun is not circular, it's slightly elliptical, and that was what was causing the irregularities of timing. They were saying it was not a planet, it was just Earth moving. So Goldstein and Frail were very careful. They're like, we really got to make sure we've taken everything into account. And so they dug deeper, and they decided that yes, there are 2 planets orbiting this pulsar. And in fact, when they dug deeper, they found 3 planets orbiting the pulsar. And this was exciting because this was the first time we had ever confirmed the existence of a planet outside of our own solar system. First time ever. We knew about our solar system. We figured there were planets elsewhere. Like I said, Bruno, back in the 1500s had thought that there were planets, but we hadn't been able to confirm it until then. Now, after they confirmed this discovery in 1992, the discovery of exoplanets started to pick up steam. Let's move to 1994. PSR B1620-26. They discovered this is a binary star system. You can kind of see it there. It's a white dwarf and a pulsar orbiting each other. And it turned out that there was a planet also orbiting those. And then in 1995, this is Didier Queloz and Michel Mayor. They discovered around 51 Pegasi a planet. And this was a big deal because the other planets that had been discovered before were around pulsars, highly magnetic, not a place where we live. This was the first planet around a main sequence star, a star like our very own sun. So in 3 years, we went from finding our first exoplanet to finding our first exoplanet orbiting around a main sequence star. And since then, we keep finding more and more and more exoplanets. So this is a little chart of the number of exoplanets we've discovered by year. You can see, there's the 1992. It turns out they actually discovered one in 1989, but weren't able to fully confirm it until fairly recently. But you know, you've got 1, 3, 1, 1, and then all of a sudden it just sort of takes off. This is partly from 2011, and in fact, this is slightly out of date because in September they just released findings of another 50 exoplanets all at once. So the thing that I want to say is that, you know, I want to talk about why did it take us so long to find out this exoplanet? You know, why did it take that amount of time? And then once we started finding it, why this kind of bounty? How is it we're able to find these stars, and why is it now we're finding them like everywhere? They're the couch cushions. They are everywhere. So we've gone from like 1 in 1992 to you know, just about 700 today. And I expect by the end of the year we'll be past 700 at the rate that we are finding. So I'm going to be talking about the methods that we use to find them, and why it took a while, a little bit of the history about why it was that, you know, Bruno and others for years thought there was planets around other stars. Why didn't we find them until 1992? That seems like a fairly long time. Astronomy had been going for a while. What happened? Don't tell me where to put that on the speakers. So, to start out with, I want to talk about the history of not exoplanets and talk about why this is so hard. One of the big problems is, if you look at, you know, if you're looking for a planet to go around a star, stars are really bright, planets are really dim. So when you're looking, you know, far away out into space, you've got a really bright star, really big planet, it's hard to see. And then, you know, at those kinds of distances, they're separated by distances of milliarc seconds or less, so really tiny angular amounts between where you're looking at the star and where you're looking at the planet. And that made it really difficult. And so what people had to do was look for them indirectly. Instead of trying to look and say, there, I see an exoplanet, what they had to do was say, all right, let me look for the effect that the exoplanet has on the star. That mainly means gravity. And this is something that astronomers had, you know, they've been doing this for a while. So let's go to 1790. This is Jean-Baptiste Joseph Delambre. He was an astronomer who computed the orbit of Uranus. And Uranus, thank you. I'm glad I just put text on the picture. For those of you who don't know what Yotzi is, you should look that up. Anyway, he computed Uranus's orbit around the sun and predicted it, you know, for years and years going out, but it was not following that prediction. So in 1841, John Couch Adams said, you know what? That deviation, the way that Uranus is moving around the sun, the fact that it is deviating from our predictions, come on in. Plenty of chairs, pick your favorite one. If you hate it, you can leave. I won't make fun of you. The fact that it was changing, you know, John Couch Adams said, that could be another planet. It's possible that there's another planet further out than Uranus, and that's what's dragging it around and changing where it's supposed to be based on, you know, versus our predictions. So he starts looking for it. And in fact, in 1845, 1846, Adams and a guy named Romain Leverrier, there he is, they independently predicted where this new planet should be. And, you know, they used Newton's laws. They said, okay, Uranus is moving like this, it's not following our predictions. Where would that next planet be mathematically? So these two guys worked it out, figured it out, and indeed, in 1846, Johann Gottfried Galle found Neptune, where these guys said it would be. So this is a case where they took mathematical laws, Newton's laws, worked through it and said there's a planet here, and lo and behold, once they knew where to look, they were able to find the planet. Now, this does not always work, because this is an indirect kind of measurement. You're guessing, well, this planet, or, you know, in later cases, these stars are being dragged around by another planet. And that's not always the case. So here's Mercury. Mercury has a really elliptical orbit. Sometimes it's near the sun, sometimes it's far away from the sun. And the perihelion, the point of the closest approach, moves. So imagine this ellipse. That ellipse is slowly moving around the sun. So it starts out there, and then goes to there, and goes to there, and keeps going around. So in 1859, Leverrier had good success predicting where Neptune was going to be. So he said Mercury, the fact that its orbit is clocking around like that, has to be because of another planet, the planet Vulcan. There is a planet inside Mercury, close to the sun, that we will call Vulcan, that is dragging Mercury's orbit around. So people looked for this, and looked for it for years, and there were a lot of astronomers who said, I think I see Vulcan, I think I see the planet inside Mercury, orbiting close to the sun. But they were never able really to confirm that. And that's because Vulcan doesn't exist. It turns out in 1916, Einstein was able to explain this. Mercury's perihelion and advancing like that is actually a relativistic effect. If you work through general relativity, it turns out that's what's supposed to happen. It's not another planet. Vulcan does not exist. So I tell this story to point out, one, we know how to find things based on their effects on other things, astronomically speaking. But two, that's not always perfect. You're not always going to get the right answer. So it's easy to get this wrong, and a lot of people have gotten this wrong. In fact, what I want to start out by doing is talking about all the times that people got it wrong, to sort of help you understand how difficult it has been to find planets outside our solar system. And before I go on, one of the things that they tell guys like me, if you're going to be popularizing science, it's important to tie it to some sort of pop culture phenomenon. You know, Star Trek, science of this, science of that. So that's what I'm going to be doing on this, and I'd like to start out by talking about, like I said, exoplanets that weren't. Come on, surely there's a brony somewhere in here. No? Ah, wrong audience. It's okay. I guess that's later in the day. All right, so exoplanets that weren't actually exoplanets. We will start off in our gallery with, and this is going to be hard to see, 70 Ophiuchi. There it is. It's a little star. It's about 17 light years away, so, you know, astronomically speaking, in our backyard. And Johann Heinrich von Mattler in 1842 was tracking its, as it moved across the sky, and discovered that there were irregularities in it. So, just like the case with Uranus's irregularities of orbit, people looked at 70 Ophiuchi and said, you know what? There's a planet there. That's what's happening. The planet orbits around the star and sort of drags it back and forth. So, there's got to be a planet there. So what that meant is people wanted to take as accurate a set of measurements of 70 Ophiuchi's position to try to figure out information about this planet that was supposed to be dragging it around. And the biggest claim of an exoplanet actually came in 1895. This is Thomason Jefferson Jackson C. And luckily he has a mustache to match his name. So he and his sweet mustache decided that 70 Ophiuchi had a planet around it. He was measuring the irregularities and said, that's got to be a planet. So the problem was a lot of other astronomers did the same thing, and they said it's got to be a planet, but their measurements of irregularities were different than C's. Everybody had different measurements. They said, well, obviously it's moving and it's not where we expect it to be and not where we predict it to be. But everybody had different measurements. And in fact, there was another astronomer, Forrest Ringwald, who published a paper shortly after C. C is the only guy, a lot of people had irregularities, that it may be a planet, we don't have enough information. C staked his reputation on the idea that there was a planet orbiting around 70 Ophiuchi. And when another astronomer, in fact, published a paper saying, you're full of it, you're full of crap, there's no way this could happen because I worked through the mathematics. 70 Ophiuchi is actually a binary star system, two stars orbiting around each other. The planet that you say is doing this, it would be mathematically unstable. The system would fly apart. The planet would go zipping off into space. C got so angry, he started publishing. He was like the cranky old man publishing op-ed letters in a newspaper. He sent letters to scientific astronomical journals denouncing this other astronomer and saying he was full of it, and eventually had a little bit of a breakdown and then got shipped off someplace else because he was a royal astronomer. So they didn't get rid of him, they just sort of like shunted him off to the side. And in fact, turns out he was wrong. There is no planet around 70 Ophiuchi, to the best of our knowledge. And there were other people who were looking for those. In 1943, Dirk Grable, there's a great name, and Eric Holberg took 10 years of data, 10 years of photographic plates, because of course, at that point what they were doing is, aim a telescope and a camera at the sky, take a picture, take a picture, take a picture, take a picture, build up all these pictures, measure where the star is in them. This is pre-computers, and they thought there were irregularities. But W.D. Heinz, he was an astronomer at Swarthmore who, in the late 90s and early 2000s, went back and looked at a lot of these flames. And so he looked at 70 Ophiuchi and decided that, and I quote, "Unusually large systematic errors in the visual measures of the 19th century were to blank proceeds mistake." Because in the 19th century, they're just using eyeballs. They're only starting to barely use photographic plates. And in the 1943 measurements, they were never able to reconfirm them. So, 70 Ophiuchi, not an exoplanet. Now let's move. There we go. Barnard star, right up there. It's even closer. It's a red dwarf. It's 6 light years away, so we're really in our backyard. And there it is a little closer. This is Peter Van de Kamp at Swarthmore. It turns out, by the way, Swarthmore has an excellent astronomy program, and so Swarthmore astronomers pop up in my stories a fair amount. So this is Peter Van de Kamp, and he started taking photo plates with Barnard's star in 1938. And over the next 25 years, collected a giant stack of photo plates measuring where Barnard's star was. Now, he thought there was an irregularity in its orbit. But on the photo plate, that irregularity translated into a difference of location of a micron, the width of a human hair. So what he would do is he would get 10 people, probably his grad students, to come in and look at the plate, and they would all 10 of them would make independent measurements, and then he would average them. And he did this for 25 years. And after 25 years, he said, I've got this giant stack of data. I'm convinced there is a planet around Barnard's star. There are irregularities in its motion across the sky. Gotta be a planet. So other astronomers, so he made this announcement in the 60s, and in the 60s and early 70s, other astronomers said, this is fabulous. Like, this was a big deal. This was showing up in, Time and Newsweek kind of deal. Everybody was like, this is it. We found the first planet outside our solar system. Other astronomers could not repeat what Van de Kamp had done. And then, some people went back and looked at all these photographic plates and discovered that every star on these plates had the same wall. It turns out, sometime in, I think it was the 50s, they pulled the telescope apart to clean it and upgrade it and change motors and all those kinds of things and put it back together. And Van de Kamp had not taken that properly into account. He tried, but he hadn't gotten it right. So all of the stars appear to be wobbling like Barnard's star. And in fact, W.D. Heinz again, that Heinz was Van de Kamp's hand-picked successor at Swarthmore. And Heinz, this was the big thing. Swarthmore was really excited about it. Here's a college with the professor who had discovered the first planet outside the solar system. And Heinz went back and said, I can't discover it. I cannot reproduce this. Nobody can reproduce this. And I imagine that made for really chilly faculty dinners. And in fact, Van de Kamp went to his death saying, if anybody thinks this isn't a star, I invite you to take 25 years worth of data and make all of your graduate students try to find and measure what the star is. He said there has to be a planet around Barnard's star. There was no planet around Barnard's star. We have yet to find any evidence of that. Now, as a side note, I mentioned C and I mentioned Van de Kamp, who both went to their death saying, I have found an exoplanet. Scientists are human. When you make a big discovery like that, you stake a fair amount of your reputation on that, and it's really tough to go back and say, I was wrong, sorry guys. Earlier I was talking about how in '91 there were some astronomers who published a paper in Nature, a pretty prestigious journal, published a paper saying, I have found an exoplanet around the pulsar, and then had to come back in 1992 and say, it wasn't true. Well, when Lynn, one of the astronomers, made this announcement at the meeting of the American Astronomical Society. He stood up, gave a paper, said, here's all the methods that we use to recheck our figures, and it turns out there isn't any deviation in the pulsar, there is no exoplanet. He got a standing ovation. So sometimes scientists get it right, and sometimes scientists are willing to let go. So I tell you these stories, part because it's funny, I can make fun of mustaches and things like that, but also finding exoplanets is hard. This is not easy science. There's a reason why it took us until 1992 to find the first planet outside our solar system. This is macho science that they were doing. Like I said, one of the problems is if you're trying to find an exoplanet, stars are bright, planets are dim. It's just hard to see. You can't just look and see that planet orbiting around the star. Like I said, they're very close together. From those kinds of distances, you're talking milliarc seconds of angular distance or less. So generally, you've got a bright star that masks the planet. The planets are too close to be resolved. You just look at them with a telescope. You're talking about trying now to see a planet dragging a star around it as it orbits. Those are small effects. It's really hard to see those unless it's really supermassive. And then you've got the problem with Earth and Earth's atmosphere. Go outside, look at the star, it twinkles. That's because you've got a whole lot of air. Some of it's hot, some of it's cold, it's moving around. It bends the light, it refracts it, moves it around. So you have to take all of that into account if you're trying to make exact measurements. So, a natural question is, what changed? Why is it we were not able to find exoplanets, and starting in 1992 we were? The big difference, the thing that has made a giant leap forward in astronomy, really, computers. Once you could start using computers to automate these kinds of searches, you could do so much more. And in fact, if you remember me talking about Van Camp and him saying there was a planet around Barnard star, one of the first computerized systems in 1972 for looking at a photographic plate and identifying stars and tracking it, they used that to show that Barnard star was not having the kinds of wobble that Van Camp had been playing. So you've got computerized searches, you've got computerized models, you've got computerized everything. And that makes a big difference in finding. Another thing is, frankly, practice makes perfect. Everybody's trying all kinds of different methods to see these exoplanets. And eventually one works, and you say, aha! And then everybody uses that method. And then someone else discovers another method, and they say, aha! And so once you have something that you can do scientifically, other people can follow up with that and perfect that and do things like that. For example, 1995, Bose-Einstein condensation. This is taking laser beams and supercooling atoms using lasers until they get into a giant single quantum state. First demonstrated in 1995, won 3 people the Nobel Prize for it. You can now do this in freshman college classes. Putting the system together and doing it. Because it was really hard, and then once people discovered how to do it, it became easier. Same thing here with finding exoplanets. Once you have discovered an exoplanet using one of the methods that I was talking about, then other people can improve on that method and say, this works. Let me see if I can do it. So, let me start off by talking about those techniques. The big thing that we use to find exoplanets, frankly, is gravity. We look at the gravitational effect of the planet orbiting around the star, and we look at the effect that has on the star and the light that it puts out, and the position of the sky, and all these kinds of things. So planets drag stars around. As the Earth is going around the sun moves. It orbits around like that. Now these are small effects. These are very hard to detect. So you can't just, again, look very easily and see it moving back and forth like people tried to do in the 19th and 20th century. So you have to come up with other techniques. Now, the reason why the first ones were found around a pulsar is because it's much easier to see the effect of a planet on a pulsar. Pulsars, it's a huge magnetic ball of star. You start out with a supernova. The supernova explodes, and you end up with this magnetic core. And the thing is, angular momentum is conserved. It's sort of like, if you watch skaters, you're spinning around and they pull their arms in and they go much faster. You start off with a big star, supernova, blows everything out, now you have a tiny star, and the tiny star orbits really fast. And it's orbiting really fast, it's got a magnetic field, so it sends out this sort of searchlight of electromagnetic energy. It sends out visible light, it will send out X-rays, it will send out gamma rays, it will send out all kinds of different things. And it's spinning fast enough. The slowest pulsar that we have found, to my knowledge, spins around once every 8.5 seconds. Usually these things are spinning on the order of milliseconds, so that thing is just whipping around. So you can understand, you've got this beam of electromagnetic energy that's sweeping past the Earth really fast, so it's like pulse, 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 pulse. You can understand why, when people first discovered this in the 1960s, they thought, this has to be aliens. Aliens are sending radio signals to us, because it was like if I was keying some sort of radio transfer. And in fact, pulsars were originally called LGM. These things are super active. They are essentially nature's clocks because they're spinning very fast and they're very accurate. And they don't change except over long periods of time. Eventually, because it's sending out energy, that spin slows down and slows down and slows down. And eventually it slows down enough and it doesn't send out radio signals or whatever. But that takes a long time. It's going to take much longer than any of our lifetimes to see any of these appreciably slow down. So you can look at these and you can look at the timing, and the timing is very regular. But if you've got a planet dragging that thing around, then sometimes the pulse comes a little early, sometimes the pulse comes a little late, depending on where that planet is around there. So you take a pulsar, you look at when those signals, as it sweeps a signal past us, you combine that with very accurate clocks and time when those pulses come in. And if the timing changes, you can say that might be an exoplanet. So that is pulsar timing, represented here by this particular My Little Pony. Pinkie Pie, for those of you here. And that is how Bullstein and Frail discovered the first exoplanet in 1992. You've got this pulsar being sweeping past Earth, and there are 3 planets dragging that star around. So they use computerized models to say, well, sometimes the signal comes in a little early, sometimes it comes a little late. The timing difference is on the order of a millisecond. And the thing is, that millisecond change, I said it's because it's getting dragged around, that corresponds to the pulsar being dragged around by a velocity of about a meter a second. So that's about this kind of speed. The clocks are accurate enough, and pulsars are accurate enough that you can detect meters, a meter a second kind of change. This is pretty much a science. And in fact, the reason they were able to see all 3 of those is they were looking at changes of microseconds in that pulse. And so they plotted, and you get the cute little graphs, and you put that against the computer model, and the computer model says 3 planets, A, B, and C. That's exciting, it's nice. Pulsars aren't exactly where you want you to live. I mentioned that they've got a whole lot of magnetism, they're sending out all these signals. There's a whole lot of radiation. This is not where people like to be with radiation. Which is why people were excited about being able to discover planets around stars, main sequence stars like our own sun. So how do you do that? Pulsars are nice, because pulse, 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 and you just look for the timing change. What do you do if the star isn't nice? Well, it turns out there is a method called Doppler spectroscopy.
We gotta get this set up.
Any star sends out light, and there are gaps, there are black bands in its emission spectrum based on what kind of star it is and how much hydrogen, how much helium, how much heavier elements. Those elements absorb some of the light that the stars are giving off. So if you've got a planet going around it, it drags that thing back and forth, and you get a Doppler shift. So those lines move around. Now this is very exaggerated, but that's essentially what happens is you look at those lines, those emission lines, those blank points, and you see them moving around. And you say, well, that may be a planet dragging that star around. This is the radial velocity or Doppler spectrum method, represented here by a rainbow dash. And this is the method that Mayor and Halos used in 1995 to discover 51 Pegasi b. Pegasus, come on. So these are educational ponies. Do not make fun of the ponies. So they used this radiospectroscopy method to discover the first exoplanet confirmed around a star that was not a pulsar, 1995. And the thing is, this is the most, so far, the most productive method that we have used to find exoplanets. So if you look here, all of these sort of blue ones are the ones that we've discovered using this radial velocity or Doppler spectroscopy method. It's by far the most that you've got to work on. This is a really good method of using it. Now, there are limitations to the method. For one thing, you need a lot of signal to noise. That is, you got to be able to see the light coming out of it. You got to look for those blank spots in the emission spectrum. You got to see them moving around. And so, if the star is really faint and you can't get all of that light, that becomes difficult. The other thing is the solar system that you're looking at, the plane of the ecliptic. So, think about our solar system. It spreads out like this. You need that to be edge-on to. Because what you're dealing with, to see this, you got to have a Doppler shift. And to have a Doppler shift, the star has to move towards us, it has to move away from us. So imagine taking, if you take that and turn it 90 degrees, so you're looking sort of like looking at the top of our solar system. If you're looking at the top of one of these solar systems, you don't get any Doppler shift because the star is moving like this, and that doesn't change the light coming towards us. You need it to move like this. And the other thing is you need a big planet, and it's got to be pretty close to the star that it's orbiting. The limitations on Doppler spectroscopy, the radial velocity method, are you can see about a meter per second kind of motion. So, as a comparison, the Earth moves the Sun by about 1/10 of a meter per second. So if you're looking for Earth-sized planets, the radial velocity method is not great. So, that's why people came up with another method, because this one is good for what they call hot Jupiters, things that are about Jupiter size or bigger, that are really close to the star that it's orbiting. So, this is great. Found a whole lot of planets using this. Obviously, people wanted other methods. So, the next thing people said is, well, what happens when a planet moves in front of a star? And the thing is, it dims it. You get not quite an eclipse because obviously the planet is going to be a lot smaller in the most part than the star that it's going across. But the star's light dims just a little bit, not a lot, but a little bit. So you can look for a planet going across a star and the star's light dims. And based on that, you can say there's probably an exoplanet going across that, and that's called the transit method. So, I said 1992, first exoplanet found by a pulsar. 1995, laughed at me. 1995, first planet discovered using the radial velocity method. 1999, first planet discovered using this transit method, looking for the star that dimmed. So that is HD 209458. And astronomers discovered HD 209458b, which is a planet. And what they did is they already knew it was there using the Doppler spectroscopy. So they had seen those lines shift and discovered that there was a planet around there. And they said, okay, let's see if we can use this transit method. We can see the star get dimmer to find that planet. And in fact, they were able to do that. So they sort of reconfirmed it. And then once they had done that, then they had a lot more confidence to go and look for exoplanets, but we didn't know there were any exoplanets. So HD 209458, the transit method, they saw about a 2% drop in the star's output as that planet went around. So that's 1999, they reconfirmed it. It took until 2002 for astronomers to find the first exoplanet solely by the transit method. This is Ogle TR56, and Ogle TR56b was the planet that they discovered. And its named this because it was discovered by the Ogle project, which I'll talk more about in just a second. So, that star is 4,900 light years away, further away than you can really do the Doppler spectroscopy method, because your signals are going to drop too much. But we were able to find a planet by that transit method. So, an obvious question is how much dimmer does a star get when a planet goes around? Now, that's going to depend on the size of the planet and the orbit of the planet and a bunch of stuff like that. But generally, you're looking for 1 to 2% kind of change, which means it's sort of like, as one astronomer put it, you're a mile away and a fly falls across a car headlamp. That's the kind of change we're seeing. And, flies are, for the most part, fairly small. We're looking for very, very minute changes in the star's outlets. All right, let's talk limitations. Obviously, star, planet needs to pass in front of the star. If the planet passes above the star, from our point of view, you're not going to see it. It's got to go in front of it. And the probability that you've got a planet moving like that, obviously, gets less as you start looking at whatever solar system you're looking at, edge on. The probability also depends on the ratio of diameter of the sun to the diameter of the planet that's crossing across there. So again, the bigger, it's sort of like the Doppler spectroscopy method. The bigger the planet, and the closer it is, the better chance you've got of seeing this dimming happen. So take a planet orbiting at 1 AU, so the distance from the Earth to the sun. The probability of a random alignment producing a transit is about 0.5%. So you're not going to see a whole lot of planets. The odds are against you. But despite that, we found a lot of planets using the transit method. The other problem is you really need sort of a backup measurement. You make a measurement with the transit method, and that's probably it, but it could be a lot of other things. So ideally what you do is, if you find planets using the transit method, then you go back and you look at the light using the Doppler spectroscopy method and try to confirm your discovery. Now, the nice thing about that, so if you think about it, the Doppler spectroscopy method depends on it dragging the star around. So the more massive the planet, the more it drags the star around. So using the Doppler spectroscopy method, I can get a guess at what the mass of the planet is, but I don't know how big it is. Well, with the transit method, I'm looking at how much does the star dim as the planet goes across it, so I get an idea of how big it is, but not the mass. So if I combine those two things, I can now make a measurement of not only how large is the planet, but how heavy is it. And using those, I can start to say, well, it's a large planet, but it doesn't have a lot of mass. It's a gas giant. Or it's smaller, it's denser, it's rocky, it's a terrestrial Earth-like planet. So those two methods really work well in tandem. All right. So Doppler spectroscopy, transit method, really cool. Gravitational microwave. So imagine that you're looking at a star way back here, and another star goes in front of it. What you would think is, well, you make it dimmer because it's getting in the way, but it actually makes it brighter. What happens is the gravity of the star bends light around it. So some of the light that normally would have headed out this way ends up bending and coming towards us. So it acts just like the lens of your glasses. It takes this light that's headed out and focuses it back towards us. So you can look for a star passing in front of another star, and it gets brighter. And then if you've got planets dragging this star that's between you and the other one that you're looking at, so you've got planets dragging that guy around, then the brightness will change and fluctuate. So it's another indirect method, in this case using a partner star, to figure out that you've got planets around the star in the middle. So this is pretty cool. I'll represent that by rarity. So I mentioned the OVO project earlier. That's optical gravitational lensing experiment. This was a project with the University of Warsaw. So the OVO team really perfected the method of using gravitational microlensing to see that. And they found the first planet via gravitational microlensing. OVO 2003 BLG 235L. So what the OVA project is doing is looking at as big of a swath of sky as it can and watching all these stars and watching them get brighter or dimmer. So you can kind of understand why the OVA project was also the first one to find an exoplanet using the transit method, because they're looking for any stars getting brighter or dimmer. So they saw a star getting dimmer, they said that's the transit method, found an exoplanet. In this case, saw a star get brighter as over 2003 KLT 235 passed in front of it and said, gravitational microlensing, there are exoplanets right there. Microlensing is really good for finding low-mass planets because it's not the effect, that fluctuation in brightness. You get more fluctuation per mass than you do get Doppler spectroscopy motion per mass. But the thing is, this happens once and it ain't happening again. You know, you're picking two random stars and waiting for them to go in front of each other. So typically what happens is when you've got a transit event starting, everyone sort of picks up the astronomical background and calls everybody else, and they start making as many measurements as possible to see if they see anything happening, if they see any kind of variations that indicate that there's an exoplanet there. It's sort of like picking two people at random in the US and waiting for them to line up with respect to me and watching what happens. So you can't plan for this, you just got to wait for it to happen and grab as much data as possible and pull it up. So I've talked about all the indirect methods. Why don't we just look for the planets? You know, I mean, that's how we found Pluto. So 1906, this is Percival Lowell, and he and his sweet mustache decided that there was a planet outside of the elliptic orbit, which he called Planet X. And so in 1929, the director of Lowell Observatory, after Lowell's death, did what astronomers often do, jumped into the hands of grad students and said, take a look at this. So that is Clyde Tombaugh, who was 23 years old at the time, and he took a year taking photographs and at 2-week intervals. So he would take all his pictures once every 2 weeks, and then he would blink back and forth between them to see if there was anything moving that might be this planet X. And in fact, he did find Pluto. So, just to give you an idea, that little tiny thing there, that little tiny thing there, that's Pluto. Those are the kinds of pictures he was looking at and trying to see differences between to find Pluto. So, he found Pluto, and there it was, the next planet until 2005. Quite proud of Pluto. Sure. Pluto, no longer a planet. So, why don't we just look for them? If we could deal with the fact that this, the star has a big glow, then we could maybe see the planets orbiting around it. And in fact, it is possible. It's not easy, but it is possible. And the trick is, what you do is you go to infrared. Instead of looking at the visible light spectrum, you look at the infrared light spectrum, because the planets, especially if they're young, if they've been formed recently, are going to be hotter, and you can start to look for them. So, in fact, in 2004, the international team used the Very Large Telescope Array. So, these are very large telescopes. So they used the Very Large Telescope Array in Chile to see a planet orbiting a brown dwarf called 2 mass WJ 1207334 minus 393254. Or 2107, that's right. So they were able to find the star, this planet orbiting its star. Now, this star is a brown dwarf, and brown dwarfs are sort of, they're pale stars. Their stars are quite vacant. That means they're not putting out as much light, so it's easier to find planets around them because they're not masking the planets around them as close as much as regular stars. So, not quite a real star, but pretty good finding it around the world. They were able to find one orbiting a main sequence star in 2008. So, 1 RX J160929.1 minus 210524. Never say astronomers don't have a good sense of humor. There it is. The reason they were able to see this distance here, 330 astronomical units, 330 times the distance from the Earth to the Sun. And in fact, it's far enough out there that they spent a year or so just watching it because they weren't sure it was a planet that was orbiting. They thought it might be something sort of passing by. sort of coming from the neighborhood, like a comet state or something like that. And it was far enough away that the star's brightness didn't mask that exoplanet. So, this method right now is limited to young nearby stars, and it works best for planets that are ways out so that we don't have the problem. What would be ideal is if we could take that star's light and make it vanish. And that's where coronavirus comes from. So, Bernard Leo, 1939, he wants to look at the sun's corona. Hard to do, the sun's really bright, so he came up with the brilliant idea of putting a block in the middle of his telescope. So you put a big disk that blots out the sun, and then you can start to see the corona that's around it. And so people said, well, why can we use a coronagraph to do that? And in fact, there has been some really neat things going on. One of the problems is, like I said, the distance between the star and any planets that are orbiting are really tiny, tiny block. But people have come up with something called the optical vector vortex coronagraph. And what they do is they point the telescope dead at the star, and then you do some optical tricks to make that essentially vanish. There's this vectoring kind of stuff go. And the star's light, the thing that is dead on in the middle of the telescope, goes away. So what we've got left are a couple of planets that we can look at because the stars are this is HR 8799. We already knew those planets were there, but a team at JPL used this vector photograph to look at it and, for the first time, image the actual planets, directly see the planets around it. So that's pretty much the methods that we use for finding. I'm sorry?
So what happened to A? Did it turn out it wasn't there?
I don't know. It may have gotten voted like Pluto. So these are the 5 methods of magnification techniques that we use. We've got pulsar timing, looking for the pulsar changing. We've got alpha spectroscopy, look for lines moving. Transit, look for the planet going from the star. Gravitational lensing, wait for 2 stars to come in front of each other and then see if the light is changing as that happens. And then direct observation. To cap it off, this is LISA 581c. This is probably the most famous exoplanet going. In 2010, for those of you who are science nerds and read science news, you may have heard about this exoplanet. It's the one that is about 5 to 10 times the mass of Earth. It's a terrestrial rocky planet. And even though it's a tenth of an AU away from the star, it is a 581, it's in the habitable zone. So the habitable zone is if you're too close to the sun, then water's going to boil. You're not going to have liquid water. Too far away, it freezes and you get ice. The habitable zone is the region in between where it's possible to have liquid water, which is what we figured you got to have life. So we talk about exoplanets being in that habitable zone, sort of Goldilocks zone. Not too hot, not too cold, just right. And this was in there, and it was about Earth mass. It was terrestrial, and people said, "We found another Earth." The problem is, it turns out it's tidally locked. One side of it always faces the star, one side of it faces away from the star, which means one side is really hot, one side is really cold. So I guess if you live right in the middle, you might be and it's probably experienced runaway greenhouse effect, sort of like me. So I'm not sure I took vacation on there. If you're going to pick one in LISA 581, I take LISA 581G. It's not been confirmed yet, but if it is confirmed, we'll be in the habitable zone. So I'd like to end by talking about 2 specialized space missions that have been designed strictly to look for exoplanets. And the first one here is Granade. It's the French Space Agency. The European Space Agency teamed up, and in 2006 launched this telescope. It's using the transit method, so it's looking at a swath of the sky and waiting to see stars get dimmer. So they launched it in 2006. In 2007, 2 new planets discovered. As of June of this year, 25 confirmed planets and some 400 unconfirmed ones. So giant pile of potential exoplanets astronomers are looking. The other one, Kepler. This is a NASA mission. It launched in 2001. Now, it is in an Earth trailing heliocentric orbit. So what that means is, there's the sun, there's the Earth. It's sort of coming behind the Earth as it moves around. So it's moving away from Earth and is kind of looking out at the galaxy. There we go. And is watching about 160,000 stars. So it's watching a whole lot of stars. And about 100,000 of those are main sequence stars, stars out of our sun. But Stephen, how good is it? Well, I'll tell you how good it is. January 2010, they looked at the first 6 weeks. Okay, 6 weeks. 6 weeks of data, and discovered 5 exoplanets. By February of this year, there's where Kepler's looking. Just to give you an idea of how little of the galaxy you're really looking at in a period of time. We're looking at about a 3,000-year light cone. You have all the rest of us. Okay. So, 1,235 candidates. There are and that's only going through 2009's data. That's through September 2009. They still have all of 2010, a big chunk of 2011 to process. And in fact, you can help out. There's a website called planethunters.org where they were releasing all of this data. And in fact, there are, I think, about 5 or 6 candidate exoplanets that amateur astronomers have discovered by trolling their data that the Kepler team is making. So with the Kepler team, there's so much data, they're shoving it into the computer models and running through in this era. The computer spits out these possible candidates. Here you go. There are possibly other candidates that we just don't see. So we've got some spare time on the board. Planethunters.org. All right. So where do we go from here? One thing is better detection techniques. I mentioned the vector chronograph. There's an optical nullifier again, so that you point your telescope at a star, and the star's light goes away so that you can see planets. Robots are producing a torrent of data, so much data. We're still moving through all of that and churning through all of that and trying to analyze it and see and look for all these planets. And we're still finding exoplanets using regular old terrestrial telescopes. In September 2011, the HARPS team, it's a spectrograph that they put on looking for spectroscopy method. They just announced in September of this year 50 new exoplanets, which is why my graphs are really out of date. And the reason that, you can say, well, that's a big deal. Planets outside our solar system. The thing is, we still have a lot of questions about how stars and how solar systems work. Before we started looking at exoplanets, all the data that we had, all the information that we had about how solar systems work comes from our own solar system. It's sort of like walking out into your backyard and trying to decide how all of Earth works based on the grass that we've got. So exoplanets let us look at and ask questions like, you may remember, the planet I talked about, that's 330 astronomical units away. How did that happen? Normally, planets are much closer in. Why did that particular solar system evolve so that you've got this planet way the heck out? We're watching all of these stars. We're trying to understand, better information about how solar systems form. And that's exciting. And this is data that we did not have before. Just looking at our solar system only gets us so far. And now we've got all of this data. And frankly, we didn't know how many exoplanets you might find. One of the astounding things about this is exoplanets are everywhere. They're like in the couch cushions. They are almost everywhere we look. And so that tells us something about how the solar system, solar systems evolve, and what is the possibility of life on other planets? People sort of hand wave and there's the Drake equation, all that kind of stuff. Well, now we're starting to get hard data about the number of exoplanets that you can expect around stars, and there's lots, and what they're like. And that's all, to me, really exciting scientific information, and that's why I think exoplanet hunting is really cool. And that's all I got. Any questions?
The Hubble done anything? You found any extra things?
Yes, they have found, the Hubble team has found some. The problem with Hubble is everybody wants time alone.
I like that.
Yeah. Hubble has a lot of really good instruments, and so astronomers line up to sort of get slotted in to do that. And so exoplanet discovery shows up every once in a while, but is not the main thing. And in fact, typically, I think the exoplanets that they have discovered using Hubble have been sort of, oh, we found an exoplanet. It's sort of been an add-on to whatever it was that they were doing.
You showed 3 observatories a little while ago. Did you say that those were in Chile?
The University of Warsaw, there's one in Poland that I showed, the one in Chile, the very large telescope array, the giant one.
Yes.
A lot of those tend to be around the equator because that's a nice place to live in. And, astronomers like it where it's warm too.
So the Hubble and this other one that's I forgot what it's called. Kepler. Are they going to be maintained?
Right now.
So far?
I mean,
I know they talked about going off the Hubble several times.
right. As far as I know, Hubble funding is still good. I am not as plugged into that.
Kepler is newer.
Kepler, yes. I forget when Kepler is due to the mission. But part of it is, when you launch something like that and it starts working, you sort of try to suck all the data out of it you possibly can. And NASA, I think, has done a good job when the missions have gone better than expected of keeping. Think about the Mars rover. The Mars rovers were supposed to have what was that, a 6-week design lifetime, and instead it stretched for years. They're like, we're going to keep it going, and we're going to keep exploring, and we'll keep doing that. The same thing's been happening with Kepler and with Hubble. Hubble is a little more difficult because it's an Earth orbiting telescope, which means the Earth's atmosphere drags on it. It starts to drop down. A lot of its instruments use cryogenic cooling, and so the cryogenic liquid goes away after some time. Stuff dies on it. So the Hubble has required a lot more maintenance and upkeep and sending astronauts to there, which was really dicey. In fact, they looked at doing Hubble fixes using robots, because the problem is, if you look at the Hubble orbit, you look at the International Space Station orbit, they're not together. And so back in, I guess, 07, 08, when we were looking at the last servicing mission that they did, they were worried because that was right after the issue with the shuttle and the tiles. Right? So if you get up there and you discover your tiles are bad, you want a place to stay. So the ISS is nice because you can kind of park out there until you get another shuttle up there. The Hubble, they were going to have to just sort of sit around until they could get another shuttle up there and do a shuttle-to-shuttle rendezvous orbit that they've never done and do all that kind of stuff. So they were worried about it and tried to come up with a robotic mission. And in fact, when they went up and sent astronauts to service, they tested some robotic vision techniques and stuff like that. I got to work on, and that was a lot of fun. So Hubble requires more maintenance than Kepler does, just in general. I'm guessing they're going to run Kepler until funding completely dries up or systems on it start, like if the gyroscope starts to fail, so you can't point it accurately anymore.
Did you see those cartoons where the Mars rovers are saying, "When are you coming to get me?"
Yeah.
You got the ball here.
Sad. So cool. Anything else?
Did they discover anything on Mars rover? I realize this is not a topic. Did we discover anything in the red rocks?
Did we discover anything in the red rocks? I think what we discovered was a better understanding of Mars, because I keep using the backyard analogy because I think it's really accurate. You land Vikings on there, it's like, all right, I've looked at the ground, here's what I know about Mars. There was the question of water ice and things like that the rovers were able to do, and the fact that they rode and they were able to go further than just where they landed has given us more data about Mars and what Mars is really like. And it's really cool.
Yeah, okay, so you were talking about that extraterrestrial can be what, 10 times the size of Earth?
Up to 10, yeah.
Yeah. Wouldn't that make it inhabitable on its own? Wouldn't the gravity on that make it a little bit too rough for us to walk around on?
It depends on its size. Because the gravitational pull of the planet is going to depend not only on its mass, but also its diameter. So gravity is a question of density. So I do not remember what the gravity was going to be like on that planet. But the other thing is, NASA, like any other kind of organization, and astronomers, like any other profession, it's nice to have some attention, and things like, we've kind of discovered an Earth planet gets attention. Or if you guys saw, we discovered a giant diamond planet. That was, what, a couple of months ago? They found a carbon planet, a large portion of which is probably in the diamond structure where the galaxy is formed. And that gets people's attention, that gets the press, and that's nice to have. That's one thing that we don't know. It's hard enough right now seeing the planets that finding moons on planets are even harder. That's probably going to take the next leap in detection technology before we can start saying, yeah, we can see moons. Because right now, just seeing planets is hard. Yeah.
I guess it was like a month or two ago, I read about how astronomers had discovered like a giant expanse of H2O in space. Have you know?
Not familiar to me.
Okay.
It very well could be.
It seemed like a credible source. And supposedly it's like trillions of miles.
Really?
Like giant ocean, just floating space.
Giant frozen ocean of water.
So
Did they say where that came from? Or did they have any ideas about its formation?
no. Well, I don't know.
Yeah. The thing that I'll keep harping on is there's a whole lot about our universe we don't know. Talk about dark energy sometimes. There's just stuff we don't understand yet. There's a whole lot left to be discovered. So,
Haven't they found like when the Hubble took pictures from the top and the bottom, as opposed to out on our plane? I forgot the estimated number of universes they were saying are out there.
oh, galaxies or
Yeah.
you very well could be right. I play as an astronomer, so all of my knowledge is sort of secondhand. You're not mistaken for an actual astronomer. I just think it's
Do you know if there's like any research or practice into what the next step in planet discovery would be?
Yes, absolutely. I mentioned some of the vector chronograph and the nonlinear chronometer that the folks at Jet Propulsion Lab, JPL, NASA, are working on. That's probably the next thing is, can we advance our direct detection techniques? And then, once those get good, and the other thing is, we keep getting better at the ones that we've got. In terms of being able to measure brightness changes, stars dimming and getting brighter, and in terms of measuring the Doppler shift of lines as we get more and more accurate spectrographs and things like that, that makes it easier to see small planets and things like that. So, I don't know what the next absolute leap is going to be, and that's, I think, part of science is you get people going in all sorts of different directions. Say, I think this might work, I think this might work, and eventually something does, and then you push that technique for all it's worth. If there's nothing else, thank y'all for having me.
Well, that was actually pretty awesome.